Periodic table. A-level for WJC and Educast. Yay! So, basic things is just how the periodic table is ordered. It's ordered in terms of the number of protons in the elements, and the reason why electrons aren't used is because electrons can be gained and lost to form ions. Vertical columns are known as groups. Horizontal columns are periods. And yeah, if you were to get an element and look for ones that have similar properties, you would look for ones in the same groups. Like halogens have similar properties, and the way that electronics, the way that the shells are filled can be figured out in this table. So you have s orbitals and p orbitals in your shells, those would be subshells. So you have 1s, and then it goes 2s, 2p, 3s, 3p, 4s, 4p. I'm just going to, I forgot about 3d as well. If you draw out this table, just like that, so 4f and 5f, the way that the shells fill is like this. So you have 1s filling, 2s filling, 2p filling, 3s filling, 3p filling, and then 4s. Oh, my pen's run out of ink. I'll go to purple pen instead. 3p fills, and then 4s, then 3d, 4p, 5s, then 4d, 5p, 4f, 5d, and 5f. The reason why the 4s shell fills before the 3d is because 4s sits at a slightly lower energy level than 3d. And electrons just want to be able to sit at the lowest the lowest energy level that they can. You can also look at the electronic configuration of elements to find their position in the periodic table. So in the S block, it has elements, it contains elements in groups 1 and 2 whose electronic configuration ends in something S1 or something S2 respectively. And that is why this is called the S block, because all these elements, their electronic configuration, these ones end in S1 and these ones end in S2. This would be 1S1, this would end in 2S1, this would end in 2S2, 3S1, 3S2, 4S1, 4S2, and that's what these numbers mean as well. So this would be 7S1, 7S2. You also need to know how to write the shorthand electronic configuration, where, say you're doing the shorthand configuration of calcium. Calcium is here. It is in period 4 of the periodic table, so it would end in 4s2, but you wouldn't just, with shorthand, you don't write every single one. You don't write 1s1, 2s1, 2s2, 3p1, 3p4, 3p5, Although you wouldn't write that, you would just, if you were to have a p block element, you would just write, say, 3p4 or 3p5 or 3p6. You wouldn't go every single 3p shell. But anyway, that'd be 3 anyway. What you do for the shorthand, in the case of calcium, you look at the elements, one of the noble gases. So the noble gas that comes before whatever element you're looking at. So in the case of calcium, that would be argon. And you just put it in square brackets. Oh gosh, I'm dropping things. You put the argon in square brackets, the symbol of it, like that. And then from there, then you just do the rest of it. So you get argon, and then you just write 4s2. And that'll be it. So, yeah. The periodic table is particularly useful if you want to look at just how things fill, so you don't have to think too much about it. So you can just go across like that. So say if I wanted to work out, for example, sulfur, I would just look at the way that the periodic table is arranged and get to there. So that would end in 4. Although because of the way the shells fill, as I've mentioned, the 4s fills before the 3d, and then the 3d fills before the 4d. So this would actually be 3d and not 4d, despite the number. So you just pretend everything's shifted down. Well, shifted up, actually. Just pretend everything's shifted up. Now, oxidation and reduction, in terms of electrons transfer, you need to know about that. So, a reaction that occurs with both oxidation and reduction happening is called a redox reaction. And the way you remember what oxidation and reduction is, I use at least, and what I've been taught, is oil rig. So, oxidation is loss, reduction is gain, and that is of electrons. So if something's being oxidized, it is losing electrons. If it's being reduced, it is gaining electrons. So for an example, say you have a reaction between magnesium, copper sulfate. I'm doing this the other direction. I have more room if I do it horizontally. So magnesium as a solid reacting with copper sulfate, which is aqueous, and that makes magnesium sulfate, which is also aqueous, and copper, which is a solid. So you need to know, first of all, from a different topic, from 1.1, you need to know oxidation numbers and the rules of oxidation numbers. So if an element is on its own, like magnesium or copper, then these would be 0. And then oxygen is always a -2 unless it's bonded to fluorine or as a peroxide, but that is not bonded to fluorine or a peroxide. So that would be, because there's 4 of them, then that would actually be -8. Sulfur would, because it needs to equal 0, in this case it would be, sulfur would be a +6, so then for the rest of that, oh sorry, am I looking at the wrong thing anyway? Oh, either way, that would be a +2, and the same for this, that would be -8, that would be a +6, so that would be a +2. So now we have all the numbers of this, and if you look, magnesium goes from having an oxidation number of 0 to an oxidation number of +2, so that means that it's oxidized, so it's lost an electron and its oxidation number has increased, so it's oxidized. So, oh sorry, magnesium has been oxidized. And then if we look at, say, copper for example, that was a +2 for its oxidation number, and now it's 0. So its oxidation number has decreased, therefore it's been reduced, and it's gained electrons. So copper has been reduced. So because you have an element being oxidized, which is magnesium, and an element being reduced, then that is a redox reaction. And if an element is oxidized in a redox reaction, then that means it is the reducing agent, because it has reduced the other element in the reaction, so therefore it is a reducing agent, as it itself has been oxidized. It has reduced the other thing. So if an element is reduced, then it oxidizes the other element, so it's the oxidizing agent. So magnesium is the reducing agent, as it loses electrons to form magnesium ion, and therefore is oxidized, and copper is the oxidizing agent, as it gains electrons to form a copper atom, and is therefore reduced. So whatever gains an electron is reduced and its oxidizing number goes down, and whatever loses electrons is oxidized and its oxidization number goes up. You also need to know some trends in ionization energy, melting temperature, and electronegativity across periods and down groups. So, right. So the first ionization energy is the energy required to remove the outermost electron from 1 mole of gaseous atoms to produce 1 mole of gaseous ions, each with a charge of 1+. If you were to write that out as an equation, Bx gaseous, so it's 1 mole of gaseous atoms to produce 1 mole of gaseous ions, because it's plus, with a charge of 1+, and that also makes an electron, because it removes the outermost electron from 1 mole of gaseous atoms to produce 1 mole of gaseous ions with a charge of plus. If you were to do examples of specific elements, you just replace the x in this equation, so it would be Na, and then it would turn into Na plus gaseous with an electron. Or you could do fluorine, which does usually produce F- ions, but in the case of seeing the first ionization energy, it doesn't really matter where the elements are in the, you just do the same equation. You don't think about, usually F would make anions, it would make a negative ion. In this case, you would still make it produce a positive ion, otherwise then it wouldn't be the first ionization energy, it would just be something else. Also remember, it needs to be a gaseous, not aqueous. It needs to be a gaseous. It needs to produce a positive ion with a charge of +1, or 1+. So across period 3, so this one with sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon, the pattern of the first ionization energies, basically, as you move across period 3, it increases. So you can see sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. It goes up, although there are brief falls between, magnesium, aluminium, phosphorus, and sulfur. So, behind the patterns, you need to remember that the first ionization energy is affected by the charge on the nucleus, the distance of the outermost electron from the nucleus, the amount of electron shielding, I'll just write shielding, by the inner electrons. So say you have that there, you have a bunch of electron, you have an electron there, there's more shielding with more shells. and whether the electron is alone in an orbital or one of a pair. So, if it's in an orbital, whether there's 1 or 2. So, charge, distance, shielding, and whether the electron is in a pair in an orbital or not. They all affect the ionization energy. So, as you progress across the period, the ionization energy generally tends to increase because of the charge on the nucleus increasing, without any significant increase in distance or shielding. The reason there's a decrease from magnesium to aluminium is because the outer electron, the outer electron to be removed in aluminium is further from further from the nucleus, is in a subshell that is further from the nucleus, so it's in a 3p shell rather than a 3s shell, and that slight increase in electron shielding outweighs the increase in nuclear charge. So, yeah, it's the nuclear charge that means that it's a little bit easier for aluminium's electron to be removed than magnesium, despite the fact there's an increase in MR. So that means the ionization energy decreases because less energy is required to remove the electron and make it into an ion. There's also a decrease from phosphorus to sulfur, and that is because in sulfur the electrons are paired up in the orbital. Like from before, one of the things that affect ionization energy is whether in the subshell the electrons are alone or in a pair. And when sulfur happens, when you go to sulfur, if I draw a little table, so you have 1s, 2s, 2p, 3s, 3p. So the way these fill, you have an electron in 1s, and another one, electron 2s, and then another one, and then in 2p you get one electron, one electron, one electron between these, if you have 3, and then it fills again like that, and that requires more energy. So that's why they initially like it just one electron in each subshell, because it causes less repulsion, so there's less energy required to be in that subshell, but then it starts to fill in more. And then in 3s you have 1, 2, and then the same applies for 3p. So that would be aluminium, that would be phosphorus, silicon, and that would be phosphorus. So that's it requires a lower energy for the electrons to be in that subshell, so they're harder to remove because they like being there more. But as it starts to fill, and it has it has a full pair of electrons, 2 electrons in the subshell, then there's more repulsion. It's not so comfortable for the electron to be there, it requires more energy, so they're easier to be removed, therefore the ionization energy decreases. For sulfur, where they start to fill the subshells up with 2 electrons rather than just 1. Now as you move down a group, the ionization energy decreases, because despite the fact that down a group obviously you have an increase in your AR, so from 9 to 17 to 35 to 53 to 85, the shielding between the outer electrons and the shell, the nucleus, increases, because you have loads and loads of shells full of electrons in the shells between the nucleus and the outer electron. So that would be potassium, and that would have a lower ionization energy than, for example, lithium. Because lithium, you'd have your nucleus, you'd have the first shell, and then you'd only have a little bit of electron shielding between that shell and the nucleus. So, yeah, it's not that the nuclear charge is weaker is that it's less effective because of all of the shielding of the electron shells. So that's why down a group, ionization energy decreases, because despite the increase in the charge on the nucleus, the increases in distance and shielding outweigh the effective nuclear charge. So on descent of a group, the atom gets bigger, but electron shielding increases, which outweighs the increase in nuclear charge. Therefore, the effective nuclear charge is less. But just because the ionization energies of the groups decrease down the groups, that doesn't mean it doesn't change the laws you may have previously known about, the reactivity of metals in group 1 and halogens. Halogens still get less reactive down the group, because as the ionization energies decrease down the group, so it is therefore easier to lose an electron. They're not trying to do that. It might be easier to lose an electron, but that just means it's getting more difficult to gain an electron, because the electrons don't want to be there. They want to leave. It's easier to leave as you move down the halogens, so therefore it's harder to gain an electron, so they get less reactive. And the opposite happens for group 1. They want to be losing the electron, so as it gets easier to do that, the ionization energy decreases, because less energy is needed for them to become an ion. Then they grow more reactive, because they can easily remove that remove that electron from their shell and become an ion. Now, the trends in melting temperatures are a bit more complex, depend on atomic mass, bond type, and the type of solid structure. So, metallic bonds tend to have a higher melting point, and then giant molecular have a lower melting point, and then simple molecular have an even lower melting point. And that's because, metallic bonds, they're actually intramolecular bonds and not intermolecular bonds. They're within the molecule, not between, and intramolecular bonds are always stronger than intermolecular bonds, which are between. So metallic bonds are always going to be stronger. Giant molecular, they're still intramolecular bonds. They are just weaker than metallic bonds. They're covalent bonds, but metallic bonds are very, very strong. And simple molecular tend to be intermolecular bonds, so between the molecules, and that's even less difficult to break. But depending on what intermolecular bonds they have, it changes the melting point of them. So say if you had water molecules, they would have a higher melting point than other ones, because they have hydrogen bonds between the molecules, which are stronger than, say, van der Waals, which would be in chlorine or argon. They're quite easy to break, but as you can see here, the melting point of phosphorus is greater than that of chlorine, and that would be because of the size of the molecule. So generally you have phosphorus P4 and chlorine Cl2, and the larger the size of the molecule, the greater the strength of the van der Waals. So I'll go through them individually. So metallic structures from groups 1 to 3, like sodium, magnesium, and aluminium. Their melting points increase across the 3 metals, so sodium, magnesium, aluminium, because of the increasing strength of the metallic bonds, and that is because the charge of the nucleus increases as you go across the period, and also the number of electrons in the sea of electrons also increases. So rather than having 1 electron per proton that has a 1 plus charge, say with aluminium, you have 3 plus charge on the nucleus, and therefore 3 electrons per nucleus. They do also mention that the atoms get smaller, so you can have more protons in one area as you go from sodium to magnesium to aluminium. So therefore the attractions and therefore melting points increase because the nuclei of the atoms are getting more positively charged, the C is getting more negatively charged, and positive and negative attract together, and the C is getting progressively nearer to the nuclei and so more strongly attracted. And therefore the strength of metallic bonds increases, and then it requires more heat energy to overcome the attractions and break the bonds, therefore melting points increase. For giant covalent structures, like group 4, like silicon, they give an example of. Well, silicon has a high melting point because a lot of heat energy is needed to break the strong covalent bonds between silicon atoms. And because you're talking about a different type of bond, it isn't suitable to try and directly compare silicon's melting point with aluminium's. The 4 simple molecular elements, groups 5 to 0, so phosphorus, sodium, chlorine, and argon. So these are your simple moleculars. We have phosphorus, sulfur, chlorine, and argon, as I said. So they are simple molecular substances with only van der Waals between the molecules, so intermolecular, and their melting points will be lower than those of the first 4 members of the period, which have giant covalent structures. The sizes of the melting and boiling points are governed by the sizes of the molecules themselves, because the larger molecules, therefore the larger the molecules are, the higher the MR will be, so the van der Waals will be stronger. So they require more heat energy to break. So that's why P4 would be more, would have a higher melting point than an argon atom, because the MR is larger. So electronegativity is the tendency of an atom within a covalent bond to attract the shared pair of electrons towards itself. As you move across period 3, the electronegativity increases as the charge on the nucleus increases with no great change to shielding or distance, and as you go down a group, the electronegativity decreases because despite the increase in nuclear charge, there's a greater distance between the electrons and the nucleus, as well as more shielding, causing the attractive forces to be less effective. It's not that the charge is less, it's that they're less effective. The least electronegative elements are on the left-hand side of the periodic table, and they tend to lose electrons to form cations, so positive ions, with increasing ease as you progress down the groups. As electronegativity increases across a period, the elements tend to accept electrons and form anions, so negative elements. That's your little trend. So the more more electronegative elements is the word I want, are over here, and the less ones are over here. So the very electronegative element will be fluorine, not very electronegative will be francium, because they're at polar opposites of the periodic table. So ionization energy and electronegativity increase across a period and decrease down any group. Melting temperatures of the elements tend to increase across any period, decrease down group 1 and increase down group 2. Group 7, sorry. There's also reactions of group 2 elements with oxygen and water/steam. This is quite an interesting table that I filled out while I was being taught stuff, because it's the reducing strength part of the question that is a little bit iffy to think about. It's a bit tricky to wrap your head around. So the trend in first and second ionization energy, it basically decreases. The trend in electronegativity decreases, but the reducing strength increases, because if you're more electronegative, you're more likely to draw electrons towards yourself in a reaction. Like, say, I explained that poorly. One moment, let me gather my thoughts. So this is in group 2, so beryllium, magnesium, calcium. So on descent of the group, you're more likely to be oxidized as it becomes easier to lose electrons because electronegativity decreases. You're not going to draw an electron towards yourself so much, so ionization energy is lower because it's easier to become a positive ion and lose that electron, and because it's easier to lose that electron, you're more likely to be oxidized because oxidation is loss of electrons, and if you are more likely to be oxidized, you're more likely to be a reducing agent, therefore your reducing strength increases. Yeah. You also need to know about magnesium reacting with oxygen. So magnesium is held in a Bunsen flame and provides the activation energy for the reaction. Once it's lit, it's transferred to a glass jar of oxygen, whereby a bright white light is seen, where the bright light seen becomes even brighter. And the white ash of magnesium oxide is the only product. So group 2 metals in water, like calcium and below that, the reactivity of group 2 metals increases down the group, similar to group 1 metals, because they, same rules apply and they both form cations. Calcium and group 2 metals below calcium react sufficiently well with water, forming metal hydroxide and hydrogen gas. So, reaction between calcium and water it sinks and effervesces, which just means makes bubbles because of hydrogen being formed, and the other product of the reaction is calcium hydroxide, which is only sparingly soluble in water, so you'll observe a thin white precipitate. You also have magnesium in water, which is above calcium in the periodic table, so it's less reactive, therefore it's a slower reaction with very few bubbles of hydrogen being formed on the surface of magnesium, and it would take several days for a significant amount of hydrogen to be collected. Magnesium in steam, however, is a lot more vigorous, so there are many ways in which this reaction may be viewed in the laboratory. So you can have 200 centimeters cubed of water being boiled for 5 minutes in order to produce enough steam to displace any air in the flask. And 3 plated strips of magnesium are ignited in a Bunsen flame before being held in the steam in the flask. And the steam in this method is generated in a different method, by heating mineral wool soaked in water. However, the test tubes often crack and are ruined by the reaction of hot magnesium with glass. It's not advised. It's advised to avoid looking at the magnesium because it glows quite brightly, forming hydrogen by reaction with steam. If the hydrogen is not collected but ignited, it will burn with a slightly yellowish flame. If the magnesium oxide that forms is able to fall into the water, a little bit will dissolve, and on addition of a few drops of universal indicator to the water, it will be significantly alkaline due to the dissolved magnesium hydroxide. So, you have magnesium reacting with steam, and that will make magnesium oxide, and then if you react the magnesium oxide, which is the product of the previous reaction, then it will create magnesium hydroxide, which is alkaline, so if you add universal indicator, it will turn blue. I will be making another video starting off on the reactions of aqueous cations with hydroxide, CO3 2- and sulfate ions, because I have things to do and I don't have time. So I will do a second part to this.